So this is the DC converter. It basically takes the charge from the battery and builds it up to a higher voltage. So it's got a positive and a negative side. Each of those can go up to 270. So you have a differential voltage of 540 volts. And the voltage on here is indicated by the yeah. And that's just static. Yep. So because the system, because you use the DC converter to build up power, or to build up a higher voltage, that voltage is stored on the system when the DC converter is charged. So if the system were charged and you disconnected the batteries, there's still a lot of voltage here. Exactly. And so this warning light, there's one here and one here, will be illuminated whenever there's a dangerous amount of voltage on the system. And you can see it says, do not connect or disconnect any cable while that's lit. So you want to be sure that anytime that light is lit, you're not touching or disconnecting any cables. So if the system's depowered, the voltage will bleed off. A full voltage charge will probably bleed off in about a minute or so.
Oh, okay.
But it takes time, and you have to wait for that voltage to bleed. Is for essentially creating a tuned circuit with the loop so that you can get the step up of the voltage when you're generating an AC pulse. So what it has in it for tuning are a series of capacitors. So underneath these bus bars are capacitors, and you can see when these bus bars are connected, that means that 4 microfarads are switched into the system. So now, right now, we actually have 8 plus 12 plus 3 plus 1 plus 5. So we have 15.5 microfarads connected. And we'll change this to tune the loop. But these capacitors, or those terminals, can have up to 4,000 volts on them. So that's why they're covered in these protective plastic guards. Also, you can see there's a magnetic safety switch right there, so that if you were to make the mistake of opening this while the system is running, it will immediately depower and bleed off that voltage through bleed resistors. 4 kilovolts, 600 amps going through them. So when you're laying them out and picking them up after a day of field work, you want to be mindful to inspect the cables to see that they haven't gotten damaged or chewed by animals. And you never want to allow vehicles to drive over the cables.
Okay.
Basically, these cables are that's where you have the highest voltage and the highest current. So you just want to make sure that they're in good condition at all times. I think I will So when the batteries are connected, these now have 24 volts on them. So you wouldn't want to touch this to the metal on the case. So you just want to go straight onto the and all the connections you want to turn them until they click. Yeah. Some are a little harder than others. on is this one.
Right.
And the EMO is still depressed right now.
Right.
So before anything will turn on, you have to put that up. So you can see as soon as I turn it on, this light's on, that light's on, which means don't touch any cables. So it says to reset the tuning capacitance to 5 microfarads. So we'll stop this, and then, so if you were trying to just work with that raw data, there's nothing you can do. Let me check one thing. 250 kilohertz.
Okay. That's a big signal.
High frequency.
It's a high frequency.
It's much higher than like seismic.
Okay.
No seismic.
I thought it was supposed to be much smaller, or is that the javelin? Do you have to deal with aliasing?
No, because we sample at a high enough rate.
Right. Okay.
So let me just. Okay, so here you see the data before noise cancellation in the frequency domain. So each line here is a data record, and so like what this. So what? Yeah. Yeah, 32, right?
Whatever the pulse moment is, how many pulse moments are.
Yeah. So it's breaking out the signals as a function of depth. So it's saying this is the signal from this layer, this is the signal from, and then it'll go through and it'll fit each one of those signals as a multi-exponential decay to provide the decay time distribution. So this is like what's happening. This is the sounding curve from the first FID. And this is the sounding curve for the second FID. So the second FID, the signal hasn't recovered. You know, you can see that approximately only, you know, in some cases about half the signal has recovered. And this is with a 500 millisecond delay. So here you see it's fitting now the signals at each depth layer.